Swayam Prabha. Digital India. Educated India.
Welcome back to Real Time Digital Signal Processing course. So, last class we discussed about a little on speech coding. Today we will continue on that regarding the vocoders. So, this is the second lecture what we will have it. So, we saw that although I did not discuss the AL compounding, so which was in the analog domain. So, you can go back and then check the thing. So, we discussed little on mu law and then little on the subband coding, how we can bring down from PCM, that is 64 kilobit per second, to subband coding of 31.5 kilobits per second rate. So, today we will see about the vocoders. So, we say it is parametric coders basically, and models the vocalization of speech, and the speech sampled and broken into frames. Approximately we break it up into 25 millisecond, and instead of transmitting digitized speech, we are going to build the model of speech and transmit the parameters of the model and synthesize approximation of speech. So, we say that the first one is the linear predictive coders in this category, LPC. So, the basic vocoder model what we are going to have it. So, models the vocal tract as a filter, and then filter excitation what it is going to be done. So, how it is going to be done? It is periodic pulse, that is voice speech or noise, we call it as unvoiced speech. So, using that we will do the filter excitation and then synthetically generate the speech at the receiving end. So, the transmitted parameters are gain, voiced or unvoiced decision, and the pitch. So, if it is voiced, we have to send the pitch, and the rest of it is LPC parameters what we have used in the coding techniques. So, coming to the second part of our vocoders, we we said it is the linear predictive coders we are going to use it. So, the first is the excitation stage. So, what we are going to have is a periodic pulse, that is voice speech or noise, we call it as unvoiced speech. So, this is how the pulse generator is going to be, and we are going to provide a pitch period in this case. So, we call this as the voiced generation, and here it is unvoiced, we say it as noise generator. So, this is our excitation model what we have it. Then after the excitation model, so we have to select the excitation. So, that is going to happen here, and we will be having the gain factor G, so which is multiplied by this one. Okay. Then these are the transmitted parameters which are the ones we are going to what gain we have used it. So, whether it is voiced or unvoiced decision we will be putting it, and then the pitch if it is a voice signal, and the other ones are LPC parameters what we will be transmitting it. So, here you will be seeing that this is the excitation model output is mu of t, and how we are going to see the LPC basically. These are the predictor coefficients. So, we will be putting the linear feedback and do the summation of the two of it, and we will be sending y of t along with the parameters of LPC. These are the parameters. So, this is our vocal tract model what we are going to generate, and then we will be passing the LPC parameters to the through the channel to receiver place. So, coming back what is it example 10th order linear predictive coder, what the example shows here. So, the samples voice at 8 kilohertz and we are going to have a buffer of 240 samples, that is we are taking 30 millisecond of the data, and here the filter model is m is 10 is the order of the filter and gain considered is g, and we know that z minus 1 is the unit delay we are going to have it, and bk are filter coefficients what we will be using it in the system. So, then what happens to our impulse response h of z is given by g divided by 1 plus sigma k is equal to 1 m is the order of the filter, b k into z minus k, then our g is going to be 5 bits and then b k is going to be our 8 bits each what we can use. For the voiced and unvoiced decision, we are going to have 1 bit and pitch is represented with 6 bits. So, this implies that we have 92 bits per 30 millisecond. So, it gives this thing 3061 that is band width per second what we are going to get the thing. So, this is the model of the LPC coding, the previous one we discussed about this. This is the model which is going to be used in the LPC. This is bits per second what we are going to have, what we have to transmit totally. What we have is can achieve low bit rates, that is from 1.2 to 4.8 kilobit per second. So, the characteristics of LPC coding is quality is very low and complexity in this case is moderate, and bit rate as we have seen that it is low, and delay in this case is moderate and robustness is also low. So, quality of pure LPC vocoder to low for cellular telephony, it try to improve quality by using hybrid coders basically. So, how to improve the quality? By refining model of speech and improve accuracy of the model and improve input to speech coder. So, by using this we can modify our LPC vocoders. So, how is it? You can see that we can use the hybrid coders, that is combine vocoder and waveform coder concept basically, and we will be using the LPC modified one, we call it as residual LPC, that is REL basically, and we can use the codebook excited LPC, that is we call it as KELP. We will see in a while how we are going to use it. So, you can see that this is again 2 which is deferred. So, you will be seeing that this is the voiced portion and this is the unvoiced region, and then how the pitch is generated, what you can see the thing, this is the frame and then this is the pitch period what we call it on the y axis. So, this is how we will be generating the pitch and then transmitting in our LPC. So, how does the this thing REL vocoder looks like, that is residual excited LPC. To improve the quality of LPC by transmitting error, that is we call it as residue along with the LPC parameters. So, you have this is the input signal which is going to be buffered or windowed here, and then you will be checking that it is voiced or unvoiced decision, gain and then pitch which are getting transmitted. So, this is short time LP analysis what we are going to see that do that, and then which is going into the LPC synthesis here, and these are the this thing LP parameters which generated from here is going to be transmitted, and from the synthesis you are going to subtract from this original, and then we will be checking the residue. So, what is the error we have got it, or the residue, which also is going to be encoded along with the parameters, and then the rest of the thing, whether it is voiced or unvoiced, gain and then pitch. So, these are the 3 inputs, along with in the LPC only these 2 are going. Now, even the residue is going to be put into the encoder, and this encoded output is sent to the receiver. So, the other one is we call it as GSM speech coding basically. How does it look like? Basically GSM, we know all of us use the thing, uses a regular pulse excited linear predictive coder, that is RPE LPC for speech. So, basically what does it have? Combine the DPCM we discussed in the last class concept with LPC. So, information from previous samples used to predict the current sample, and LPC coefficients plus an encoded form of the residual, that is predicted minus actual sample equal to error what it is going to be transmitted, and the represent the signal basically which are transmitted. So, as you can see here, this is the analog speech, so which is going to be low pass filtered, and then you will be converting it into analog to digital form. So, the sampling rate used is 8 kilohertz, and in this case A to D converter has 13 bits per sample what it is going to be represented. So, what you will be getting at the output will be 104 kilobit per second samples, and then here it is going to be RPE LTP speech encoder is going to be put in, and the output what we will be having is 13 kilobit per second what it is represented in the GSM module. So, this is going with our to the input to the channel encoder. So, how the speech coding is going to happen we will see in a while. So, we said regular pulse excited long term prediction what we can have the thing. So, that is speech encoder. Here our LP is the speech coder, and LPC we know that it is linear prediction coding filter what it is going to be present, and LTP is the long term prediction which is going to have pitch plus input parameter, and RPE we said that residual prediction error which is going to be transmitted. So, what we have here is input is a 160 samples per 20 millisecond from our A to D converter. So, which we call it as 2080 bits what it is going to be transmitted, and then this is our encoder here. So, we will be converting it into different pattern, as you can see, that is 36 LPC bits per 20 millisecond, and this is 9 LTP bits per second bits per 5 millisecond, and this is 47 RPE bits per 5 millisecond. So, all the 3 which are getting generated from our GSM. So, total what it is going to be is 260 bits per 20 millisecond what we are going to have to channel encoder. So, what we are passing it through the system. So, how the coding is going to look like? The first one we have to see the channel encoder also. So, here it is going to be using class 1A. So, this is the error correction code what it is going to happen, that is 3-bit error detection, and convolutional coding, that is error correction what we will be having it. We call it a CRC basically, both detection and then error correction what we will be having it. And if it is a class 1B, then convolutional coding is going to take place, and class 2 no error protection is going to be provided in the thing. So, these are the 3 GSM this thing channel encoders are there, and what we have is tail bits to periodically reset this convolutional coder when being used. So, what we pass is 260 bits per for 20 millisecond, which is equivalent 13 kilobit per second. So, which class you are going to use is depends on the thing. So, here if it is 1A, then you will be having 1A bits, then 50 class what you are going to have, and this is the error correction 3 bit CRC what we have it. And then for class 2 you will have 182 class 2 bits and 78 class 2 bits what is going to be generated out of it. And this one goes as 53 bits because you are adding 3 bit correction codes. So, 50 plus 3 will be 53 bits. The other ones are one more whatever you have 182 class 2 bits are fed to your this thing convolution coder. So, which is has what you call it as 2 comma 1 comma 5. So, you are going to have 4 tail bits basically what it is getting added. So, which comes down to 470 bits when it is coming out of the thing, and this is the bit interleaver what you are going to have it, which combines these bits and then the 78 class 2 bits which are coming combined, and you will be getting 456 bits per 20 millisecond. As you can see from 260 you have increased to this, and then whereas in the case of kilobit per second it goes to 22.8 kilobit per second is the data rate what it is going from GSM speech coding from the channel encoder. So, you can have hybrid basically coders, that is what we call it as codebook excited linear predictive coding. So, that is problem with simple LPCs that is voiced and unvoiced decision, and pitch estimation does not model transitional speech well basically and not always accurate. So, we said that accuracy was low in the LPC. So, whether we can use the codebook excited model. So, what is that codebook approach? So, that is parse speech through an analyzer to find closest match to a set of possible excitations, that is known as our codebook, and transmit the codebook pointer plus LPC parameters. And you can see that in NA-TDMA standard what they call it IS 95 in 3G what they use it. So, the standard for this is ITU G.729 standard. So, how is it going to be? It is going to have both the things, that is here you have the vocoder, basically you are seeing the thing voiced and then unvoiced what it will be going into the codebook generation. So, from there you will be taking the codebook generated signals and it passes through the synthesis filter, and this is how the output is going to be represented. So, then if it is having a multiple excitation, so which is taken into the thing, pass through the synthesis filter, and this is our output. Then if it is a stochastic excitation is used, use the synthesis filter and then you take the output through that. So, this way you can use the hybrid model to improve upon the standard of LPC. So, this covers our this thing vocoders basically, and then in the next class we will be discussing about code excited linear predictive model. Thank you.